Tutorbox Live in conjunction with COVID-19 catch-up courses. I know, what an exciting time to be alive right now. I am Kara Blows and I will be your Tutorbox Physical Sciences tutor. I currently study at Newcastle University in the United Kingdom and I am studying biomedical sciences. It is a pleasure to virtually meet all of you, and I hope you're having a great day and staying safe. So, grab your notebook, your writing materials, the worksheets, and perhaps a coffee or water, and let's get started into our first science lesson.
Momentum is a nice subject, or section rather, and let's get to it. So, what is momentum? So it's a physical quantity which is closely related to forces. It's a property that applies to moving objects. So in order for something to have momentum, it has to have a mass and be moving. Therefore, the definition of linear momentum of an object is equal to the product of the mass of the object and its velocity. This is a definition. You should make a note of this definition and try and learn it, as definitions do pop up a good 5-10% of your paper. The formula is P is equal to mv, and you have kilograms, meters per second. All right, the equal sign just tells you the relationship is directly proportional. Momentum is a vector, and therefore it does have direction. One will be positive and one will be negative, and that's why you can have a negative and a positive momentum. However, the momentum will always be in the same direction as the velocity because the mass is a scalar. For our first example, we're going to consider a car of mass 1,000 kilograms traveling 8 meters per second east. The momentum of the car is therefore P is equal to mv, which is equal to 1,000 times 8, which is equal to 8,000 east. All right, we always have to remember your direction. Now we're going to consider a motorcycle also traveling east of mass 250 kilograms traveling at 32 meters per second. The momentum of the motorcycle is P is equal to mv, 250 times 32, which is also equal to 8,000 east. Now this might feel strange that two very different vehicles could have the same momentum. However, even though the motorcycle is very much lighter than the car, the fact that they're both traveling at such different speeds, the motorcycle so much faster, means the momentum is the same. Another important concept is change in momentum. So when an object experiences a resultant force, the object will accelerate. Thus, because the velocity of the object changes, the momentum of the object will change. This can be written as change in momentum is equal to final momentum minus initial momentum, which is equal to mass times your final velocity minus mass times your initial velocity, and you can also take out the m as a common. Example 2. You can follow along in your workbook with all these examples and make notes as you see fit. A ball weighs 500 grams and is thrown at a wall with a velocity of 20 meters per second. It bounces back with a velocity of 18. Calculate the change in momentum. So we're going to take our right as positive. We know that the ball doesn't change mass, so we draw a little ball and it weighs 500 grams, which is 0.5 kilograms. It is always helpful to draw a before and after picture just so you can get your sign convention correct. Before, the 20 is in the positive direction, and after, the 18 is in the minus direction. And so your change in momentum is equal to your mass times your final velocity minus your initial velocity, which is equal to 0.5 times 18 minus 20, which is equal to negative 19 kilograms meter per second. So what does your negative tell you? The momentum is away from the wall because you've taken positive as towards the wall. And remember, your momentum will be in the same direction as your velocity. So that makes sense. Okay, so for example 3. A boy plays a snooker ball perpendicularly towards the side of the table from which it bounces back. So our vector marked Pi represents the momentum of the ball as it travels towards the side of the table, and the vector Pf represents the momentum of the ball after it has bounced back. Which vector below represents a change in momentum? Okay, so we know it's vectors because the size of the arrow is your magnitude and your arrowhead is direction. So firstly, we're going to take the initial direction as positive. So this should actually be the other way around. So your change in momentum is equal to mass times your final velocity minus your initial velocity. Okay. Right, so your final momentum minus your initial. So we're going to take your final and you're going to minus the initial. However, the initial is the wrong way around. So we're going to flip it over, and that will therefore make the vector a positive in the opposite direction. And then the minus sign changes the direction of the vector, and we're going to get option C. However, if this confuses you, as this will generally be a multiple choice question, you can just quantify. So your change in momentum will be your final. So we're going to take this one because it's in the opposite direction. Remember, this arrow is wrong. It's going to be -5. And then this one needs to be bigger than the final. So we're going to say it's 10. And because according to your equation, it needs to be -10. And therefore we get -15. So we know it's bigger than those two. So it has to be C or D. And we know it's in the negative direction. So therefore it has to be C. Okay. Next. Newton 2 can also be expressed in terms of momentum. So remember, Newton 2 states that the net or resultant force acting on an object is equal to the rate of change of momentum. It can be stated in terms of momentum. I know, crazy stuff. The resultant force acting on an object is equal to the rate of change of the momentum. All right, sounds very confusing, but I'll break it down with a quick formula. So our resultant force, it says, is equal to your change in momentum over your change in time. All right. Why is that? So what is momentum again? It is your mass times your change in velocity. Change, over your change in time. What is change in velocity over change in time? Your acceleration. And this is a formula you are familiar with. Okay. An example of this is example 4. So a 440-gram soccer ball traveling at 60 meters per second is kicked by a player. The ball moves off in the opposite direction at a speed of 20 meters per second. If the ball was in contact with the player's foot for 0.1 of a second, calculate the resultant force exerted on the ball. Pretty straightforward. We're just going to use this formula. So we're going to take the original direction of the ball as the positive direction. Write out your formula. Always write out your formula. You do get marks for them. We're going to break that down into what we already know. Plug in your components. We know that the final is in the opposite direction, and so that's why it's negative, and the original direction is what the first velocity the ball is moving at. All right, we plug that into our calculator. You get negative 158.4 newtons, which gives you 158.4 newtons in the direction of the player's foot. You will either have your negative, so you'll either leave your answer like that. However, they do like you to take out the negative and then rewrite your equation as such, because the negative implies in direction. So if you have both, it does get a bit confusing. Alrighty guys, so that was part 1 done. Not too hard, I'm sure you aced understanding all those concepts. But just to make sure, on your worksheet you will see 5 questions, I think, and just try attempt them as to the best of your ability. Show all you're working out, and yeah, have fun with it, and I'll see you again for part 2.
So for the first question, the car's momentum is given, and we're going to know what the car's new momentum will be if its mass is doubled and it travels at the same velocity. So our momentum of our old is m times v, and we know that that p is 20,000. Excuse my bad handwriting. Alright, so for the new one, we're told that it is 2 times the mass, but it has the same velocity. So that is a common. Therefore, your new momentum is 2 times 20,000, which is equal to 40,000 kilograms meter per second. Okay, alright, so the next one. So they want to know what the velocity will be, now if we know the momentum and the mass. So P is equal to mv, so we know that the velocity is the question, so we've got P over m is equal to v, so it will be 60,000 over 2,000, and so got 30 meters per second is our velocity. They don't give you any direction of that, so you could just say in the same direction as the momentum. Alright, so our third one, they want to know how the momentum changes if we increase the weight and decrease the speed. So initially, we've got the truck of 6,000, times 80, which gives you 480,000. And the new one, its mass, it's saying it's loaded with, so our total mass would be 7,200, and it will be traveling at 60 kilometers per hour. Oh no, that's wrong. Alright, so for the third one, there was a little bit of a trick question, because it mentions kilometers per hour, however we know momentum is in meters per second, and so you have to convert that. So for the first one, we write a formula, and we've got mass of 6,000, however your velocity is not 80, but a quick way of doing this is 80 times 5 divided by 18, which will give you 200 over 9, or 22.22, times that by 6,000, and you get 133.3. Then the second one, we know the mass is 7,200, and its speed will be 60 times 5 divided by 18, which is 120.123. So our second momentum is less, and that makes sense because we increased our mass, which should increase that, but we did decrease our velocity as well. Alright. Then the next one, so they want to calculate the force. So we know F res is equal to change in momentum over change in time. And what is change in momentum? It's change in velocity times mass. So our final velocity is 30, and our initial is 25. There's no change in direction, so it just stays like that, and our mass is 1,000. All right. Over time, we know that it says 5 seconds. So that gives us 1,000 newtons. All right. Then following on from that 1,000 newtons, the second question says, assume the direction of the initial velocity is positive. So that is your initial. And the answer you obtain from the above problem is negative. What is the direction of the exerted force? So remember, your velocity is going upwards, so it's going away from the Earth. So therefore, if your force is negative, it means your force is going towards the Earth, or away from the rocket, however you want to look at it.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 49. It's on momentum, which is just the product of the mass of an object times its velocity. In 1895, a train was headed towards Paris. They were a little bit behind schedule, didn't apply the brakes in time, and it came shooting out through the train station. What was their problem? They had too much momentum. And if you were to ask somebody what is momentum, they'll probably come up with a pretty good definition that would fit in physics. Momentum is always going to occur if we have an object that's in motion. And if you want to calculate it, you simply multiply the mass of the object times the velocity of the object. The greater the mass, the greater the velocity, the greater the momentum is going to be. And so if we want to change our momentum, what could we do? Well, we could decrease the mass, we could increase the mass, or we could change the velocity. What's the easiest way to change the velocity is to apply a net force to that object. If we apply a net force to the right to this object, what are we going to see? We're going to see an increase in momentum towards the right. Let's say the object is moving towards the right and we change the net force on the object. What's going to happen? It doesn't happen instantaneously, but what we'll see is a change in momentum that reflects that net force. And so if we define momentum, the equation is P equals mv, where we're multiplying the mass of an object times the velocity of the object. So if we have this cart here, a 1.0 kilogram cart, and it's moving with a velocity of 2.0 meters per second, figuring out its momentum is really easy. You simply multiply 1.0 times 2.0, and so our momentum is going to be 2.0 kilogram meters per second. And so if we add velocity to the right, we're going to increase that momentum. Now, one thing that you need to remember is that the net force on an object is going to affect that change in P, or that change in momentum. And so let's say we have an object like this, a cart that's at rest. It has no momentum, but we apply a net force to it. How would we do that in a physics lab? We're just going to connect it to a weight. And so now we're going to apply a net force to the right. What's going to happen to our momentum? It's going to increase to the right. What happens if we increase that net force? If we double the net force on the object, what's going to happen? We're going to increase the momentum more quickly. Let's say we triple it, we're going to see an increase in momentum to the right. And so it's a direct relationship between the net force on an object and the momentum on that object. But let's make it a little bit trickier. Let's say that object is moving now towards the left, but we're applying a net force to the right. What's going to happen? Well, eventually what's going to happen, let's watch, is it's going to slow down and then it's going to start to accelerate to the right. And so even though it was moving to the left, as we apply a net force to it, eventually that momentum is going to move in the direction of the net force. Now these are pretty easy problems because we're just looking at one dimension. But when you were growing up like me, you probably played video games like this. And so if I turn the ship and move it in this direction and blow up an asteroid, it's all momentum. But I would find myself playing asteroids like this. I'd be moving in one direction, but I'd be applying a force in another direction. In other words, my momentum is in that direction, but my net force is in a totally different direction. What's going to happen to that? Well, it doesn't happen instantaneously, but what's going to happen is that ship is eventually going to move in the direction of the net force. And so did you learn to justify the data we need to collect to show that the net force eventually impacts the change in momentum? I hope so, and I hope this was helpful.
Hi everyone, so I hope you had a good chance to attempt those questions. The answers are as follows. So number 1, it is 40,000 kilogram meters per second. Answer 2 is 30 meters per second. You can define a direction, it would just be the same as the momentum, but they don't really give you one. Number 3, your first one will be 133,333,33, and the second one will be 120,000. Yeah. And then the second part, the force would be 1,000 newtons, and the second one would be down or towards the earth because your initial velocity is up away from the earth. So part 2 is going to be dealing with a slightly different concept, mainly conservation of momentum. Right, so this applies to 2 objects, and the gist of it is that the total momentum of 2 objects before they collide is the same as their total momentum after they collide. This can be summed up into a definition, one that you should also know for your exams, which is the principle of conservation of momentum, generally linear, is the total momentum of an isolated system always remains constant. Okay, fairly straightforward, but slightly complicated, so I'm going to go into a bit more detail on the bits of that definition. So a system is the small parts of the universe being considered for the problem. Everything outside of that is called your environment. Therefore, your internal forces occur within the system, and the forces occurring outside are called external. Your isolated system is one that has no net external forces acting on it. In this context, it means that the only force acting on the objects in the system are the forces that the objects exert on one another. So the objects collide. Based on Newton 3, you know that they're equal and opposite forces, and those are basically the only forces that we're talking about. Okay, so another fun thing is collisions. Very, very basic. Another 2 definitions just to help you are elastic and inelastic. So elastic is where the collision has occurred and the total kinetic energy is constant, whereas inelastic is when a collision occurs and kinetic energy is lost. So inelastic is, for example, when a tennis ball hits the wall and becomes deformed while in contact. That deformation results in a decrease of kinetic energy. Another thing is something can be perfectly inelastic, so that is when 2 objects become stuck together. For example, I'm pretty sure all of you at one point or another have dropped your phone, probably more than once. And you know that if you drop it and it bounces, or if you drop it on the side, the crack, if it does crack, is a lot smaller than, I'm pretty sure, when you've dropped it and it's just landed flat down and didn't even bounce. And I'm pretty sure everyone knows those cracks are always the worst. And that is just because all that momentum has transferred into losing the kinetic energy, and that has just resulted in that really, really nasty crack. Okay, Another important point. Momentum is conserved in both collisions. Don't think because you're losing energy, momentum's not conserved. That's not what that means at all. Another thing, draw separate pictures for before and after, and choose a sign convention. Drawing your pictures will also help you assign things with the correct sign, and trust me, if your examiner sees a physics accurate, whatever that means, diagram, they are more likely to give you marks for that diagram, even if you go somewhere wrong in the calculations, just because you've actually thought of the principles. Alrighty, so there's going to be 3 examples we're going to deal with, all different types of collisions, and hopefully this will be able to clarify and help you separate each type of example. So example 5, ball A is moving to the right with a velocity of 8 meters per second, colliding with ball B, moving to the left at 12. After colliding, ball B continues moving to the left at 1 meters per second. Determine the velocity of ball A after the collision. Okay, and they both weigh 250 grams. We're going to take the right as positive. So before, we've got A moving to the right at a positive 8 meters per second, and we've got ball B moving to the left at a negative 12 meters per second. After, however, ball A, we don't know what the velocity is, but ball B, we know is still left, so it is still minus 1 meters per second. Your answer to this will tell you which direction ball A is moving to. I'm sure you can kind of guess based on the numbers, but we're going to work it out anyway. So total momentum before is total after. You write out your formula. Subscripts can be pretty helpful in this situation, just because you've got masses and initial velocities and final velocities of both. And then from there, we plug it in. You've got plug in the weights, plug in the initial velocity of 8 and negative 12. Masses don't change, and your final, we don't know the final velocity of A, so here you can drop the A subscript because we are only looking for final velocity and you know it's of A. However, you can keep it if it makes more sense to you. We know the final velocity of B is minus 1. So we work that out and we get a final velocity of minus 3 meters per second. So all that minus means is it is that direction, which is to the left after the collision. Example 6. This is another collision example, like I said, except in this case, instead of being separated, they unite. Okay, so trolley A weighs 4 kilograms, moves with a velocity of 3 meters per second, colliding inelastically with trolley B. What does inelastically mean, remember? We lose. Okay, energy, not momentum. And that trolley weighs 2 kilograms, however, it was at rest, so that tells you your initial velocity is 0. The trolleys unite. When a problem means they unite, that generally means then that your final mass will then be the 2 added together. Okay, calculate the velocity of the 2 trolleys after collision. We're going to take the right again as positive. So we know the 4 kilogram trolley is moving at 3 meters per second to the right, and we know that the 2 kilogram trolley has a 0 velocity. Afterwards, they become 6 kilograms and we don't know the velocity. So same thing as before, total before is equal to total after. Your mass times your initial velocity of A plus your mass times your initial velocity of B will equal the total mass of them together and your final velocity. So you plug in everything and you get a final velocity of 2 meters per second. You have to give your direction. Since it's positive, it goes to the right, which makes sense. If that goes there, you know that it's going to keep going. Last one, an explosion or separation collision. So this is kind of like a reverse collision, if that makes sense. So a bullet leaves a gun with a velocity of 200 meters per second. The mass of the bullet is 50 grams and that of the gun is 1 kilogram. Calculate the recoil velocity. Means the opposite, excuse the typo. Okay, so to the right, we know that the initial velocity of the gun is 0 and it weighs 1.05 kilograms with the little 50-gram bullet. The velocity afterwards, we don't know. That's the recoil velocity. So if you think about movies and stuff, when you shoot a gun, you know the gun is going to go that way. So you are expecting a negative velocity. It's very important to think logically on these questions. If your answer is something that doesn't make sense, you may have made a mistake. So it always helps to be intuitive. And then we've got the little bullet and we've got its weight and its very, very fast speed. Okay, total momentum before, total after. We know that before, because the velocity is 0, your momentum is 0. Okay, we plug it in, so we've got the mass of the gun times the final velocity, plug in the bullet's information, and then we get a final velocity of minus 10. So it's 10 meters per second in the opposite direction to the bullet. Okay, which makes sense. It means it's going to go that way, and that's why it's called recoil. Okay, I'm going to let you try this one on your own.
Alright, so I hope you've had some time to attempt this one. So, we've got a trolley. Its mass is unknown, so we're just going to place it as m. We know the velocity before this collision was 10 meters per second. And we know that when the trolley has the mass piece on top of it, mass after will be your mass of the trolley plus your 2. Your velocity is 8. Alright, so we do everything we've almost done. Your total before is equal to your total after. So, we've got your mass before times your velocity before is equal to your mass after times your velocity after. Alright, so we don't know the mass of the before, so we're just going to place an m. We know the velocity is 10, and we know the mass after will be your m plus 2, and we know your velocity is 8. So, we've got 10m is equal to 8m plus 16. Move that 8 over. We've got 2m is equal to 16. So we've got m is equal to 8 kilograms, which is the correct answer.
It's not a matter of whether or not we can. Everybody can, but not everybody will. How to turn nothing into something. How tangible are ideas and imagination? Ideas that become so powerful in your mind and your consciousness, they seem real to you even before they become tangible. Imagination that is so strong that you can actually see it. You can actually see it. If somebody cannot see it when it is not here, then it will never be here. Start looking into the future of what you would like to accomplish, where you would like to go, the person you would like to be. Decide what you want, and then act as if you already had it. And that is to believe that what you imagine is possible for you. So the first step is to imagine what's possible. Second step, to believe. Now here's the third step, and that is to go to work and make it real. You now go to work and make it a movement. You make it tangible. You make it viable. You breathe life into it, and then you construct it.
You have a lot to offer. The fact that you're still here means that your business is not through yet. People don't do what they know in life, but what they do is they operate within the context of the vision they have of themselves.
So write and draw and build and play and dance and live as only you can. Make up your own rules. The rules on what is possible and impossible were made by people who had not tested the bounds of the possible by going beyond them.
You must change what's possible for you. You, and only you, are the subject that impacts the burning desire in your imagination. You are living and feeling as if your future dreams are a present fact.
Will it be easy? No. Will it be challenging? Yes.
So you got to prepare yourself. You've got to develop yourself. As long as you're breathing, you got some more work to do. There's something else for you to achieve. Guess what? You're going to make some mistakes. You're going to make a lot of mistakes.
So now go and make interesting mistakes, make amazing mistakes, make glorious and fantastic mistakes. Break rules, leave the world more interesting for your being here. Make good art.
It is possible to start with nothing and become something.
Hello again, everyone. I just wanted to say a huge congratulations for finishing the lesson, and I hope the concepts, examples, and the questions were beneficial, and I hope you engaged as much as possible with the content. I hope you will tune again soon, as this was Tutorbox Live in conjunction with COVID-19 catch-up courses. Stay safe, everyone, and I hope to see you guys again soon. Bye!